This presentation is on 9.3 and 9.4 for AP Chemistry. Recall in the last topic that we discussed bond dipoles, looking at bonds in which one of the atoms like the electrons a little bit more than the other one, and so the electrons hung out around that atom a little bit more, creating a dipole, a negative end to that side and a positive end to the other side. Just because a molecule possesses polar bonds does not mean that the whole molecule is polar. So we can talk about bonds being polar, and we can talk about molecules being polar. Um, they do relate to each other, but they do not go hand in hand. If one of them's polar, the other one's polar. If one of them's not, the other one's not. You can't judge it by that. You have to take into account some of the geometries that we learned about in the last couple of sections. So here we have carbon dioxide. We have the couple of bond dipoles with the oxygen sitting here liking the electrons a little bit more than the carbons. So we set up these bond dipoles towards the oxygens, negative oxygens, positive carbon. But you can see the overall dipole moment will be neutralized. It'll be zero because they're both pulling. Both of these oxygens are pulling at the same rate, and so it's a symmetric molecule, and so the whole molecule will be nonpolar. The whole molecule is nonpolar. So by adding individual bond dipoles together, you can determine the overall dipole moment of the molecule. Will that molecule be polar or not? Let's take a look at the water molecule. Here we have two OH bonds. The hydrogens are less electronegative than the oxygens, so oxygen will be more negative, hydrogens will be more positive. And you can see with the two of them we have there that they will add up together, and you'll get this overall dipole moment of this molecule, looking like that. Here's just some examples of polar and nonpolar molecules. The whole key is symmetry. If something is symmetric, then it will be nonpolar, or yeah, it will be nonpolar. If it's not symmetric, it will be polar. So let's take a look at our first example here, HCl. This is not symmetric, so it will be polar. The chlorine is pulling the electrons more than the hydrogens, so we're going to set up that polarity. Here's BF3. This one is nonpolar. It's symmetric. All these fluorines are pulling the electrons at the same amount. Note that boron is one of those exceptions where we only need 6 valence electrons around it. So keep that in mind when determining polarity of any boron-containing molecules. Another nonpolar, carbon tetrachloride. Sitting here again, the carbons in the middle and the chlorine are all pulling the same amount in all directions. It's symmetric. That molecule is symmetric, so it will be nonpolar. Now if we look at some polar molecules, starting off with this bottom one here. Here we have the chlorine, which will be pulling the electrons more than the hydrogen will. And so since it is not symmetric, you will have a greater negative charge on the chlorine end. Same thing with this NH3, this ammonia molecule. What's going to be missing here are these two unshared pairs of electrons in their area that they're going to be hanging around. It's going to be a big area like that where they're hanging around, and that's why these hydrogens are being pushed down. They're being pushed down, and so they will you will get a negative end up here at this negative end by that nitrogen. Let's take a look at a couple of sample problems. We're going to determine whether these are going to be polar or nonpolar. Let's take a look at the first one, BRCl. First thing to do is draw the Lewis structure. BRCl. Finish our electrons around there. which we're not going to do for the rest of these, but just know that if there's an atom that doesn't have the dots there, that the octet is filled. So here we have a polar molecule. This one's going to be polar because it's not symmetric. If you draw a line down the middle, it's not symmetric. Chlorine is more polar or more electronegative than bromine. So that's going to be a negative charge. We're going to have a positive charge on chlorine. Excuse me, a positive charge on bromine. Now let's take a look at SO2. We have a couple of resonance structures. We have one like that. We have one like this, with a lone pair of electrons on that central atom there. And we also could possibly have this resonance structure. Let me change that up for a second here. Make this a little bit better for us. All right. So those are the three resonance structures. These two will be bent. These two molecules are bent because we have these lone pairs of electrons up here pushing these atoms down. And so those will be bent and they will be polar. In this case, this one will be linear and it will be non-polar. So it just depends on which resonance structure we're going to be looking at. Oh, this one, SF6. If we look at the structure for this, it's going to have the expanded octet with these fluorine molecules all around, and it will be symmetric. Since it is symmetric, it will be non-polar. So if you have something symmetric, it's going to be non-polar. Look at a couple more. Now we're talking NF3. Draw this one here. N, F, F, and F. And again, we have this lone pair of electrons on that central atom. Again, making this big electron domain, pushing these atoms down, causing it to be trigonal, pyramidal. Since it's trigonal pyramidal, it will be polar. Key thing to remember, if you have electrons on that central atom, it will be polar because that will distort the shape of it. These electrons here, this big electron domain, will push the other atoms aside, making it non-symmetric, and you'll end up with a polar molecule. Let's do this last one, BCl3, Cl, Cl, Cl. Here again, boron needs 6 electrons around it, around that central atom. So it's not going to have any lone pairs there. So this one would be non-polar. Because that one will be trigonal planar. Trigonal planar, and so it will be non-polar. That ends that section. Let's go to 9.4, overlap and bonding. This is what actually happens in a chemical bond. What happens to those orbitals? Those electrons move in those areas. We have the sharing of electrons with the adjacent atoms. And then the atoms will approach each other, and the orbitals will overlap in a manner similar to this. So if we have two hydrogens approaching each other, the orbitals will overlap, and here's a hydrogen bonding with a chlorine. Here's a couple of chlorine where those orbitals will overlap, those overlapped regions there. You can have minimal overlap. You can have a lot of overlap. There is a preferred distance for all of our bonds here. We're not going to get too much into that. We learned that last chapter with some of our bond lengths, but this is why it happens. This is why those bond lengths are relatively consistent like that. It's because of the repulsions of the electrons and also the nucleus from the other nucleus and the attraction of the electrons with the nuclei. So an increased overlap brings the electrons and nucleus closer together while simultaneously decreasing electron repulsions. So here's our example of this. Here we have the atoms that are far apart. When they come together, they start to come together, you will decrease this repulsion. You'll decrease the repulsion, so the energy will go down. Energy is going to go down, which is a good thing. And at some point, they'll reach their optimal distance apart, and that's what we're looking for, that optimal distance. If they get closer than that, then you're going to run into the two nuclei repelling each other. And that's going to raise the energy at that point. You can see if it raises quite quickly, because when these two nuclei start to come together, they are going to be not liking each other. They want to get further apart. So that optimal distance right there, that's how we measure the bond length. And that is all we have. Hopefully you learned a lot from this section.